The problem from GATE Physics 2015 reads as follows. In a Hall effect experiment, the Hall voltage for an intrinsic semiconductor is negative. This is because N is approximately equal to P, where N is the electronic concentration, P is the hole concentration, N is greater than P, mu E is greater than mu H, where mu E is the mobility of electrons and mu H is the mobility of holes. Or option D, Me star is greater than Mh star, where Me star is the effective mass of electrons and Mh star is the effective mass of holes. Have a look at how does a typical Hall experiment setup looks like. So this is a semiconductor bar which is intrinsic. So what do we mean by intrinsic? When we mean intrinsic, we mean that the concentration of electrons is equal to concentration of holes is equal to the intrinsic concentration Ni. This expression is valid for intrinsic semiconductors. And a current I is flowing through this semiconductor because we have applied an external bias which is denoted by the potential Va. The field is applied in the vertical direction, that's the Z direction. We know that the Hall coefficient for an intrinsic semiconductor is given by this formula that's written on your screen, on the left of your screen. Now, we know that for an intrinsic semiconductor, N equal to P equal to Ni. Let's put this value here, okay? So, I'll get Ni mu H square minus Ni mu E square divided by E Ni mu H plus Ni mu E whole square. Now I can take Ni common from the top and so it will be mu H square minus mu E square divided by, I can also take Ni common from the bottom, so it will be E Ni squared, it will be mu H plus mu E whole squared. Now I can write this, Ni get cancelled, so I'll get 1 over Nie. Mu H minus mu E whole square can be written as mu H plus mu E times mu H minus mu E divided by mu H plus mu E whole squared. 1 mu H, this gets cancelled, and so I get RH equal to 1 over Ni times E mu H minus mu E over mu H plus mu E. Now this is the expression that we get for an intrinsic semiconductor. Now note that in an extrinsic semiconductor, RH is simply minus 1 over Ne. And just by looking at this sign and by looking at this number N, we can, just by measuring the Hall coefficient, we can get the extrinsic carrier concentration. We can't do that here. Since RH is dependent on carrier concentration, intrinsic carrier concentration Ni as well as mobilities. So we just by measuring the Hall coefficient, we cannot simply get the extrinsic carrier concentration. We cannot get the value of Ni simply by measuring the value of RH. We also need mu H and mu E, and that's a complex exercise. So this is one thing we learned, that in an extrinsic semiconductor, Hall coefficient does not directly give the carrier concentration. Okay, now let's move forward. Let's do one more exercise. Since we are interested in Hall voltage, we know that RH equal to Hall coefficient is defined by this, and Hall voltage, this E Hall can be written as H Hall over the width W, and J, the current density, can be written as current I divided by W into T, the cross-sectional area of the semiconductor slab, times B. W and W gets cancelled, so we get V Hall times W divided by IB. This will give us as V Hall equal to RH times Bi over W, and I'll replace the value of RS that we obtained here. So I'll get Bi over W, right? And RH is 1 over Nie times mu H minus mu E over mu H plus mu E, right? So this is the expression for Hall voltage that we have obtained for an intrinsic semiconductor. Now let's move ahead with this expression, and let's try to analyze what can we say about the Hall voltage based on just on this expression. Now this was the expression. Note that Bi, sorry, it will be, okay, so W gets cancelled, it will be T here. I'm sorry, so this will be T. So this is the expression that we got for Hall voltage. Okay, now, so you can clearly see that the Hall voltage being positive, this is a constant term, right? The Hall voltage being, it's not zero first of all. So Hall voltage is not zero. Why? Since typically mu H is not equal to mu E. So first observation we can make that. Now, is it negative or positive? So it is negative or positive, that will depend whether mu H is greater than mu E. So if mu H is greater than mu E, we will get a positive Hall voltage, right? It's as if that semiconductor, even though intrinsic, is behaving like a p-type because it's a positive Hall voltage. On the other hand, if we get mu H is less than mu E, this implies we will get a negative Hall voltage. But we cannot conclusively say just based on this expression that V Hall is positive or negative. However, if we are given in the question that mu H is less than mu E, this means if mobility of electrons is greater than mobility of holes, it's definitely Hall voltage, or vice versa. If we are given that it's a negative Hall voltage, then we can definitely say that the mobility of electrons is greater than mobility of holes. Now, one more thing, we know that mu E, or let's say mu E equal to tau E times m star, right? Tau is the relaxation time and m is the effective mass. Now, even if we know something about mu, we cannot say conclusively about effective mass m because the relaxation time is also there. So please note that even if you can conclusive, let's say even if you can see mu E is greater than mu H, that does not necessarily mean me is less than mh. Why not? Because the factor tau is also there. See this. Hence, even if we have a comment on the mobility, we cannot conclusively say anything about the effective mass. Coming back to the question that we were given, we saw that the expression for Hall voltage was Bi upon TNIE mu H minus mu E over mu H plus mu E. So we saw that the Hall voltage was not zero. It's only zero when mu H is greater than mu E, and we are given in the question that it is indeed negative. So if this quantity is negative, all these quantity are positive, right? So this means that mu H minus mu E is less than zero, and that would mean mu H is less than mu E, right? That's the only case in which we have Hall voltage negative. So this is the correct option. Now, before we finish, I told you that mobility is tau E by m. Even if we have a relation about mobility, so mu H is less than mu E, let's put it. So tau H, electronic charge E over mh star is less than tau E, electronic charge E over me star. That's directly a result of this. So E and E gets cancelled. Now note that we cannot conclusive, so let's find the ratio of mh star over me star. So mh star over me star is less than tau H over tau E. Now we cannot say anything about this quantity mh star over me star because it depends on the relaxation times, and the question is silent about it. So we cannot conclusively say anything about the ratio of effective masses, which the option D talks about. However, we can only talk about the mobilities because that's directly dependent on the Hall voltage. So only C is the correct option. We cannot say anything about D. Only C is the correct option, and obviously N is equal to P and is approximately equal to P. We know that this is equal to Ni, but that's not the cause for the negative Hall voltage. Please note that. So only C, mu E is greater than mu H, is the correct option. Thank you for listening.